After the presentation of assessing existing structures, we might need strengthening. So Eurocode, this new generation of Eurocode includes the FRP materials, fiber reinforced polymers, in the document as an annex, an informative annex, which is Annex J. And I'm going to give an overview of strengthening concrete structures with FRP laminates. And this is a summary of the paper included in Hormigón y Acero that has been written by Ana de Diego, Luis Torres, Pedro Madera, and myself. So here we have the overview of the contents that I'm going to go through. First of all, I would like to introduce you to this type of material, to fiber reinforced polymers, which are a composite material formed by a polymeric matrix, a resin, that might be thermosetting or thermoplastic, usually is thermosetting. And this matrix is reinforced with continuous fibers made of glass, carbon, basalt, or aramid. And since the most common commercial product is with carbon fibers, the Annex J is only focused in CFRP, which is carbon fiber reinforced polymer. So this type of material, the FRPs, were related to other industries such as sports, aeronautics, automotive, and they were introduced in the construction sector in the 1990s for strengthening structures to restore or increase their load-bearing capacity in order to face or to overcome the drawbacks of steel plate bonding, which was another technology introduced in the late 60s that consisted on bonding a steel plate to the tensile face of a structure. And these steel plates had some inconvenience, some drawbacks that were corrosion of the steel plate and also their weight. So to overcome this inconvenience, FRPs were introduced in the construction sector for strengthening because they have high strength to weight ratio, high stiffness to weight ratio, a high durability because they are not susceptible to corrosion. Also, you don't need scaffolding, you reduce the labor cost, but in addition, they still have some drawbacks because they are still expensive. They might be degraded if they are submitted to high temperatures, but right now they are included, since we have more knowledge about this type of material, they are included in Annex J, which is informative. And they are included in two different configurations. We can strengthen by externally bonding the reinforcement to the tensile face of the concrete element, or we can use another configuration, which is called near surface mounted reinforcement, that consists on performing a slot cut in the concrete cover. We fill this slot with epoxy resin, and then we put or we include over there the FRP reinforcement. There are also other techniques related to FRP, such as textile reinforced mortar, where the matrix is cement-based instead of a polymeric matrix, or we can also pre-stress this type of reinforcement to reduce cracking or achieve another advantages, but those techniques are considered not enough developed in order to be included in this annex of Eurocode. In relation to the regulations or the existing guidelines, in Europe we have several different guidelines related to strengthening with FRP. There is a German guideline, an Italian, a British, a French, Swiss, a Greek guideline. And also in 2001, it was published an FIB bulletin, FIB Bulletin 14, that was a guideline for the first time in terms of using this type of material as a strengthening. This guideline was updated in 2019 in the FIB Bulletin 90, including all the new knowledge related to this type of material. And also this FIB Bulletin would like to serve as an additional background to this Annex J, because it's quite parallel to the text given in Eurocode. So entering inside Annex J, we will start with the basis of design, materials, and structural analysis. The first point is that the FRP are linear elastic up to failure. So the design tensile strength of this type of material will be the ultimate characteristic strength affected by an environmental factor and also the safety factor that is for persistent and transient design situations might be in between 1.3 or 1.4, depending if it's pultruded and prefabricated or a wet layup system that is built on site. So in relation to the structural analysis, the members that are strengthened with this type of material should not be analyzed using linear elastic analysis with limited redistribution or plastic analysis because they are linear elastic up to failure. So let's move to the ultimate limit states. We will start with bending with or without axial forces. And if we would like to design a flexural strengthening system with FRP, first of all, we need to check if the structure without any reinforcement, the structure by itself is able to withstand its self-weight, because if we have an accidental loss of the FRP, the structure must be able to resist. So once we have done this verification, we can design the flexural strengthening system with the FRP by applying equilibrium and compatibility equations, but we should be very careful because the FRP might debond. Okay, once the flexural and shear cracks appear and open and propagate, it might debond, and we should check debonding. And later on, we will see how to check this possible debonding that has been occurred in many experimental programs of the current knowledge. If we move to confinement, it's well known that by confining a column or an element that is subjected to axial forces, we can increase its bearing capacity. And the FRP might be used for confining the columns. And the only point is that the ultimate capacity of this structure confined by FRP is governed by the tensile failure of the FRP. The only point is that the tensile strength is slightly lower than the tensile strength that we have when we do a tensile test with this type of material, because the multi-axial stress state of the column, also because we have some stress concentration in the round corner of the columns. And here we have a formulation included in Annex J in order to obtain this increment that we can have in the concrete strength, considering different configurations, circular or rectangular columns, because the confinement is more efficient in circular columns than in rectangular ones. And this formulation is based on Laman 10, 2003. We can also strengthen in shear with different configurations that I will show you in the next slide. But the main problem, again, might be the debonding of the FRP in certain configurations, especially in U-shaped configurations, the one that are not completely wrapping the section. You can see debonding once the critical shear crack appears and propagates, as you can see in the pictures on the right-hand side. So we have two configurations allowed in this Annex J, the closed wrap, which is wrapping the transverse section, or the U-shape configuration. They might be continuous or discontinuous. And in order to design this necessary area for shear strengthening, we need to obtain the shear strength. We need to check if our shear stresses are lower than the shear strength of the strengthened element. And the shear strength of the strengthened element will be the sum of the tensile strength of the unstrengthened structure plus the contribution of the FRP. This contribution of the FRP the formula is quite similar to the contribution of the transverse reinforcement. The only point is that the definition of the shear strength of this strengthening system, that for steel transverse reinforcement, we say that the shear strength is the yield strength of the steel, but here the FRP does not yield, it's linear elastic up to failure. So how do we define this strength? It depends on the configuration. If the FRP is completely wrapping the section, it will depend mainly on the tensile strength of the FRP, but affected by two factors. One is 0.8, and the other one depends on the corner ratios that you apply in the corner of the section when you apply the FRP, that you round the corner here in order to avoid failure at this point. And for the open system, for the U-shaped system, the formulation depends mainly on the possible debonding of the FRP, and it's quite complex. And it considers the anchorage of the laminates above the critical shear crack. If we move to serviceability, we need to control cracking and deflections. We need to control deflections because the FRP usually has a lower modulus of elasticity in comparison to steel, and sometimes it might govern the failure of the system. Even the main purpose was to design this strengthening system for ultimate limit state purposes. In relation to service, if we would like to control deflections, the formulations are the ones of the main annex. And for cracking, the only comment is that if we strengthen a section with a CFRP laminate, we will see that if we continue applying load to this element, we will see some intermediate cracks in between the existing ones, but they are with a lower crack width, so they are not really important. And now we can move to the bond issue, which is the main point in this type of strengthening system. We can see that the bonding may occur in two different points of the element: at the laminate end, which is an anchorage issue, or in between flexural or shear cracks along the whole element. So we will need to check both types of debonding. The first one will be called end debonding, and the other one intermediate crack debonding. For end debonding, the only point is that we need to obtain an effective bonded length of the FRP, and this effective bonded length should be placed once we don't need, after the point that we don't need, or the section where we don't need this strengthening system, sorry. And we can obtain with this effective bonded length with two different types, two different methods, a refined one or a simplified method. The refined is more similar to that of the German guidelines, and the simplified is more similar to the Italian guidelines.
Eva, 2 minutes.
Yeah, I'm almost at the end. So for intermediate crack debonding, there are two different approaches in the literature. One consists on limiting the maximum CFRP strain or stress at the most loaded point. And the other one, which is the one included in Annex J, is a little bit more complex, but a little bit more exact also, that consists on limiting the increment of tensile forces in between each pair of adjacent cracks. And this is based on the German guideline and in the formulation of Pink and Zilk. And the only point is that we need to calculate the tensile stress at the position of each crack, and then calculate the increment of tensile forces in between both points, and finally compare with the shear strength. That's all. And finally, the conclusions: strengthening existing concrete structures with CFRP adhesively bonded systems has been incorporated for the first time in Eurocode provisions in the form of an informative annex. That is like the first step. It is Annex J. In this annex, we have design provisions for strengthening existing reinforced or pre-stressed concrete structures in flexure, in shear, in confinement, with passive, externally bonded or NSM systems, considering mainly that the CFRP is linear elastic up to failure, and the possibility of debonding, which is one of the possible failure modes that it's not observed in conventional reinforced concrete or pre-stressed concrete structure. And that's all. I would like to acknowledge all the projects that have been funding when I went to the meetings of the task group one, and I would like to thank you for your attention. Thank you very much.